Okay, so well, let's look at what's gonna happen when you spread the solutions on top of flame. Okay, so imagine that in a FAA you have a nozzle, or we call it nebulizer. So basically, nebulizer is something that can like turn droplets, turn your like liquids into aerosol. So aerosol means small droplets of liquids. Okay, and so when the droplets encounters the flame, this type of reaction might happen. So originally in a solution, let's say you have calcium ion, and remember whenever you have a positive charge ion, you always have a counter ion. Okay, so in this example, the counter ion is chloride. So together, you have a calcium chloride in aqueous phase, and when the droplets go into a flame, it becomes gaseous phase of calcium chloride, and then the reaction proceeds. You get the element calcium and the element chlorine, right? And specifically for the calcium, it might undergo excitation. Okay, excitation. So there's a dynamic balance between the ground state calcium and the excited state calcium. And of course, there are always some other side reactions, including, number 5, we call it oxide and hydroxide formation. Or number 6, ionization. So the key point here is that there are so many reactions happening, when you spray the liquid solution on top of the flame, right? And what you need to do is to get an optimal temperature. And this optimal temperature would allow the maximum formation of our target, which is calcium 0. Okay. And then we just shoot it with the right wavelengths, and these wavelengths can be absorbed by this guy. Right? So for FAA, remember, the lamp need to have a specific wavelength. That's the reason why it comes to a FAA. Whenever you want to measure some species, you need to change a lamp for it, the corresponding lamp for it. 所以在那个 FAA 里面最常做，我们就是说你要测某一种金属，就要换灯管。为什么要换灯管？跟它对波长，某种特定的波长，比方说钙，它呢会calcium 0会吸收某一种特定的波长，那是因为刚好这个波长可以让它 ground state 到 excited state， 但这个波长不会被拱，因为它们的这个 electronics configuration 不一样，好，所以这为什么就是要换灯管的原因在这边。Okay, so well anyway, the key point here is that need to find an optimal temperature to allow the maximum formation of the calcium 0. Okay. So right. So, and this is just a brief recap, for you guys to again to understand the differences between atomic absorption spectrometry and atomic emission spectrometry. So, for absorption spectrometry, we base on the absorption of your target elements, and for emission spectrometry, we need to find a way to get your elements to excited states. And when the electrons is returning from the excited state to ground state, it emits lights. We measure the light intensity. Okay, we measure the light intensity. So here comes the question again. So in which spectrometry you need to have an external lamp, light source? In which spectrometry you definitely need an external lasers。问题就是说，你看这两种不同的这个光谱仪，哪一种里面一定会有光源？ Light atomic absorption spectrometry need to come with an external lamp. The lamp is providing the wavelengths, and these wavelengths can be absorbed by the target elements. So in the case of emission spectrometry, an external light source is not necessary because, we can use other energy source to get the element to excited state. For example, we can use heat, we can use electricity, and we can use plasma if ICP OES is the case, right? So I kind of like introduce it already. For absorption spectrometry, when it comes time that you want to quantitation, we use Beer's law. Basically, when we have the absorbance, we know that absorbance is proportional to the concentration. Absorbance is proportional to the concentration of your target elements in the solution. So that's how we quantify it. How about emission spectrometry? Well, we measure the light intensity emitted from the excited elements. Okay, so here I represent the intensity. So when we measure, we have the measured intensity values. It is proportional to the concentration. Okay, so what about qualification? Qualification means we want to identify what they are. We want to identify what they are or what the solution might contain, what elements the solution might contain. Okay, so in this case, if we want to do qualification, which spectrometry is better? Is it be absorption spectrometry or is going to be emission spectrometry? So the answer is that, in this case, if you want to do qualification, we normally use atomic emission spectrometry rather than atomic absorption spectrometry. That's because for atomic emission spectrometry, what you can get is like the fingerprints of the elements. Well, I'm going to come back to explain it in the next slides. But at this point, try to keep in mind, when you want to do qualification, qualification means you want to identify what elements might inside your solution. Okay, so in this case, we prefer to use atomic emission spectrometry rather than atomic absorption. And that's because in emission, a series of spectral lines characteristic of the elements of interest is identified. And let's look at the this slide. So I found this YouTube video pretty useful. It kind of explain the detail and the working principle of atomic emission spectrometry in pretty detail. So here you have a flame source, and let's say this is a sprayer, a nozzle or something. Like you spray a solution of sodium. Okay, you spray a solution containing sodium ion on top of the flame. And here you have a slit. A slit is like narrow channel for the lights to pass through. Okay, so when you spray the solution containing the target element of interest, you will see an emission spectrum. Okay, so that's because, in the case of sodium ion, when it encounters the flame will allow some reaction to happen, and you'll have like the sodium to be excited. You have the excited sodium, and when the electrons on the excited sodium return to the ground states, it emits the lights. Okay, emit the lights, and this mixture of lights would enter a prism. So again, the function of a prism is to separate lights with different wavelengths. Okay，prism 就是三棱镜哦。那大家知道三棱镜的功能就是去把不同波长的光给分开来，这可以吧？哦，那你可以想象一下，在这边这个 flame，这个刚我们讲的这个在火源上面，你只要控制好温度的话，你可以得到要么就是这个 ground state 或者是 excited state。所以在 emission spectrometry 这个 case 里面呢，你需要得到 maxima， 你先希望得到比较多的这个 excited state 的那个 species。为什么？因为当它回到这个 ground state 的时候，它会 emit lights。Okay, get back to here. So, when the excited state's electrons returning to ground state, it emits the lights, and again, because of everything is quantized, the emitted lights wavelengths only contains certain wavelengths, and the prism is used to separate these lights. So eventually, you will see a pattern like this. And for sodium, the pattern you can see is something like this. And for potassium, the lines you'll be able to see will be like this. So we call this kind of spectrum lines the fingerprints of your elements. So based on the spectral lines, you are able to identify what could be inside your sample. So does it make sense? And do you guys still remember why the emission pattern looked like this? 大家还记得为什么这个 emission pattern 会长这样子吧？我们上礼拜有讲到哈。So in previous lecture, when we are talking about the emission spectrum of hydrogen, it looked like this. Emission spectrum of hydrogen. It looked like this, and this corresponds to the n equal to 4 to n equal to 2, or other like these lines represent the Balmer series. Okay. So when the excited electron is returning from n equal to 6 to n equal to 2, so you got these lights. And when the excited electron is returning from n equal to 3 to n equal to 2, you got this one. Okay, and you can calculate the energy gap. With energy gap, you should be able to know what the wavelength is. Okay. So that's the reason why it comes to quantification. Usually we use atomic emission spectrometry rather than atomic absorption. All right, so after the quick introduction of the these two types of spectrometry, let's go into flame and flameless graphite furnace atomic absorption spectrometry. And in these slides, it basically shows you guys the key components inside FAA or GFAA. So first of all, you see a light source, right? A light source, because FAA and GFAA is atomic absorption spectrometry. So the light source is used to provide the light for quantification purpose. And the central parts, you have the energy source. So the energy source here is to, like, as I say, the key reaction happened here. And by controlling the right temperature, you can obtain the maximum, like, element state. So for furnace, of course, I mean for FAA, here it would be a flame or a fire. How about flameless? In GFAA, what is the energy source? To generate heat, you can use flame. Alternatively, in the case of flameless GFAA, what could be the energy source? Okay, so remember, GFAA means graphite furnace atomic absorption spectrometry. So the heat source or the energy source here is the graphite furnace. What exactly is a furnace? Furnace means高温炉。Furnace 高温炉，但我不确定这边用 furnace 为什么，反正它就 furnace 中文翻译叫高温炉。So anyway, so graphite furnace means that the key components is made of graphite, and we know that graphite, the structure of graphite is like this. Okay. So that's the structure of graphite, and basically this guy is conductive. So when you employ like electropotential, electricity onto it, it acts as a resistor. So when you employ the voltage on top of it, it generates heat. Okay, it generates heat. It acts as a resistor, so it generates heat. And as a result, the temperature increased. Okay, so using this one, we can supply the sample with external heat, and the function is similar to the flame. Okay. So before I go ahead, in the case of FAA, when you want to have a flame in the laboratory, how do we do to generate a flame in a machine? And in the laboratory, how do you generate like flame? You burn something, right? So what is the thing you use to burn? A sign，缺。所以为什么这个 FAA， 如果大家去看这个 FAA 机器旁边，通常会有一瓶这个它的燃料讲燃料乙炔，它就是在这个FAA 里面去做这个火焰，因为燃烧你需要的东西可以烧吧。那这个 assign 就是 assign 乙炔。So in the case of GFAA, the assign is no longer needed because what you need is electricity. By employing the voltage on top of a graphite, it generates heat, and the temperature can easily reach like 2,000 or 3,000 K. Right? So similar to FAA, in the case of GFAA, the heats provided by the graphite also allow this kind of reaction to happen. Okay. A key point here is that by controlling the right temperature, you maximize the formation of the desired elements. So in the case of GFAA and FAA, you want to have a ground state elements. Okay, and following but the furnace or flame, we have monochromator. So again, monochromator is here to like filter out the lights you don't want, and then allow the lights you desire to pass through it. And later, you have a detector, and this detector is responsible for measuring the intensity of lights. And for readout, it means a computer to receive the signal. Okay. So to sum up, in FAA, the temperature supplied by the flame range around 2000 K to 3000 K, which is relatively low. And in the case of FAA, we use air as acetylene, or nitrous oxide acetylene as the fuel. In the case of flameless graphite furnace, you just apply a few volts to make heat on graphene surface, and this is because of the resistance. 这个电，因为这个 graphite 它有电阻嘛，所以它这个你加通电之后呢，它就开始产生热然后温度就会上升。那大家记得在 GFA 或 FA 这个温度，我其实不晓得 GFA 温度大概多少，但是在这个 FA 里面，它中心的温度大概2000到3000 K 那可能要去控制一下温度，可以哪一个条件、哪一个温度以下会得到最好的效果。So again, I found this video is pretty useful. You may go back and then Google this YouTube channel, Talk Board, kind of explain the emission spectrometry. 大家有空回去可以看一下它解释的蛮清楚的。Right? So the third machine or third instruments I'm talking about today is ICP. So ICP is an acronym for inductively coupled plasma. And the full name for ICP OES or ICP AES is ICP Atomic Emission Spectrometry, AES. Okay, so here. And sometimes we refer it as ICP OES. And please keep in mind that they are the same thing. They are the same instruments. Sometimes we use AES, sometimes we use OES, but they are identical. They are interchangeable. And nowadays, using ICP OES is becoming a predominant tool in environmental analysis for metal. Yeah, I would say ICP MS or ICP OES, they are like the predominant tool compared to traditional used FAA. So, well, to come back to ICP, the key term in the ICP is plasma. Again, plasma is the heat source, similar to what we have in the case of FAA and GFAA. In the case of FAA, we use flame as the energy source. And in the case of GFAA, we use graphite furnace as the energy source. In the case of ICP, we use plasma as the energy source. So, well, so basically, plasma is an ionized gas, and this ionized gas is at extremely high temperature. Extremely high temperature. So the temperature is is about like 2000 K. So compared to a relatively low temperature we found in the case of FAA. And what is plasma exactly? 电浆 plasma. 电浆是什么? What exactly is plasma? So basically, plasma is the full state of matters beside gas, liquid, and solids. Okay. I'll spend some time to explain how we generate plasma. But usually in the case of ICP-MS or ICP-OES, we need to supply it with argon gas. So argon gas is the gas we use to generate the plasma. Okay. So briefly speaking, we have argon gas, so gaseous, and if you apply it with temperature, high temperature, I'm talking about really high temperature, way above 100 degrees or something. And in this case, argon will become ionized, and then you have electron. So imagine that, like in a chamber, you have a lot of argon gas, and for each argon gas, you have an electron in the outmost orbital. So when you supply it with like really high temperature, the electron got stripped off, but the electron is not gone. The electron is still flowing like around the nucleus. Okay, so the argon stream become a mixture of argon plus and electron. Okay, so we call this kind of states the plasma. It's the four states of an element. 所以这个是我们讲的这个物质的第四态这个电浆态那它这个电子跟这个argon plus 呢它们就相处在一个 mixture 里面。Okay, so well, let's take a look at this video. It briefly introduces what exactly a plasma is.
You may have learned about the three states of matter, solid, liquid, and gas in the previous lesson. Did you know that there is a fourth state of matter, plasma? In this lesson, we will learn about plasma. Let's start by thinking about ice. When ice is sufficiently heated, it melts to form water. It has therefore undergone a change of state, from a solid to a liquid. Recall that in solid, all of the particles are closely packed in a fixed position, and therefore has a fixed shape and volume. The particles in a liquid are still touching one another and are able to move around each other. Therefore, a liquid still has a fixed volume, but it takes the shape of their container. What is the change of state that occurs when water is heated to 100 degrees Celsius? Pause, think, and continue when ready. The answer is water evaporates from a liquid to a gas, in our case, water vapor. The particles in a gas are further away from one another and take the shape and volume of their container. For certain substances, if we continue to apply heat to their gaseous form, another change of state could occur. These substances can go from a gas to a state of matter called plasma. For this change of state to occur, very strong heat must be applied. When heat is sufficiently strong, the electrons are stripped from their respective atoms, creating free electrons and positive ions. Although they are both negative and positive particles, plasma is neutral overall, as there are equal amounts of oppositely charged particles. Since free electrons are present, substances in plasma form can conduct electricity. This is what separates a gas from plasma. All gases cannot conduct electricity, but plasma can. Naturally occurring plasma include lightning and the northern lights. If we were to go far beyond planet Earth, stars also exist in plasma form. In fact, stars are really just hot balls of plasma. Plasma can be found in fluorescent light bulbs and neon signs. When an electrical current is passed through the mercury vapor in fluorescent light bulbs, it heats up the gases sufficiently to strip the electrons and to create plasma. Plasma screen TVs are made possible
I'm gonna stop here.
in this state of matter.
So this is basically the concept of the plasma. And later on, when we talk about the working principle of ICP-MS, we'll realize that the plasma is used to get the elements excited, right? So let's take a short break, and coming back, we should be able to finish the this chapter. For those of you who haven't received your midterm, it's in the front desk, and remember to give it back to me by the end of today's class. So, after knowing the what plasma is, let's come back to the talk about the key components in the ICP OES. So, of course, the key components in an ICP OES is something called ICP torch, or ICP torch, and ICP torch is kind of the center part for generating the plasma, And imagine that you have plasma generated here, and when you introduce the sample, this is your water sample, and it got pumped into the machine, and when the pump is pumping the water into the nebulizer, again, nebulizer is a spray, and it kind of turned the water solution or water sample into aerosol. And for small aerosols, it go into the ICP torch, while the large droplets go to the west. Okay, so now we know that through the nebulizer, the aerosol containing your target analytes is reaching the ICP torch, and when it reaches the ICP torch, when it encounter with the plasma, the collision between the plasma and your target analytes kind of excited your target elements from ground state to excited state. Okay, so let me repeat it again. When the aerosol containing your key target elements, the collision between plasma and your target analytes kind of get excited. The plasma excited your target analytes. So later, when the excited like elements is returning from the excited state to ground state, it emits lights. So you have a spectrometer or detector to detect or to measure the intensity of emitted lights. Okay, so does it make sense? Okay， 简单的说，这个 ICP mass 它最主要有一个 ICP torch。那这个 ICP torch 呢，它是负责产生 plasma 的地方。好，那 plasma 它就是你刚大家知道哦，它就是一个 mixture of positive ion 跟 electrons。So it features high energy. It features high energy. 然后接下来你的样品打进来呢，它被雾化之后呢，它就进到这个 ICP torch 里面去。然后当这个你的这个droplets 跟 plasma 接触的时候呢，这个 plasma 会把你的这个你要侦测的这个 key elements， 你有兴趣的金属，它就把它从 ground state 弄到 excited state。好，所以接下来呢，后面呢就有一个 detector， 它去侦测，这个 excited state 回到 ground state 所发出来的光的 intensity， 所以你可以借由这个量测这个 intensity 的高低，然后来知道就是到底你的这个 target analyze 的浓度有多少。So come back to the key components of ICP-MS. We have external supply of argon. So argon is used to generate the plasma. So the way we generate plasma is by something called a Tesla coil. But that's not a key point. What you need to keep in mind is that ICP torch is somewhere we generate the plasma, and it features high energy. And the collision between the plasma with your target analyze is going to excite it from ground state to excited state. Okay, so basically you can see here, the energy in the plasma is transferred by collision of the positive argon ion with the atoms of interest from the sample. So this collision kind of transfer energy and then get the target atoms to be excited. So here's another video showing you guys how it works in ICP AES. So take a look. So this is auto samplers, and auto samplers inside you have a pump, and the pump is in charge of transferring the sample into the nebulizer. So the central part here is the ICP torch. So the way we generate plasma is, when you supply it with argon. Okay. So argon is going to the system. And when you reach to the ICP torch, you have a radio frequency power. And then the spark from the Tesla coil is going to generate plasma. So remember, plasma is a mixture of electrons and positive charge ion, and it features high energy. So this is your sample, imagine that it contains three different atoms or ions, basically. So when you reach the plasma, becomes excited, and when the excited atoms is getting back to ground state, you release radiation, which is light. And inside the detector is a whole bunch of mirrors. So basically, in the following video is showing you guys, how to prepare the standard calibration curve. Well, anyway, I'm gonna stop here. So, that's the working principle of ICP OES. So again, if you look at the components of ICP OES, you don't need to have a lamp inside because we rely on the emission from the excited atoms or excited elements. Okay, the very last slides, I'm gonna skip this one. Please go through it by yourself. So, this is the configuration of AA or FAA. So, well, we already introduced it, so I'm going to skip this one. Well, second to the last chapters in this chapter in this semester. So in chapter 10, we'll be focusing on chromatography, or chromatographies. So, what is chromatography? In previous lectures, I talk about GCE a lot. I talk about HPLC a lot. I don't remember if I used IC as an example before, but for GC, HPLC, IC, they are all machines based on chromatographies. Okay, so the C in HPLC, GC, IC is chromatography. GC, HPLC, IC, that's chromatography. The C represents chromatography. So for chromatography, it's actually the methods for separation in which several chemicals to be separated for subsequent analysis. Okay. Again, chromatography, the main purpose of using chromatography is to separate different compounds from your samples. So why do we want to separate them? You might want to ask, why do we need to separate them? It sounds a stupid question, but I'm not sure whether you guys know the answers. Why do we need to separate them? Can we just, directly like quantify it? Well, the answer is, in most cases, you won't be able to directly, quantify a specific compound without separation. Okay, well, let me repeat it. In most cases, for compounds in environmental sample, you won't be able to directly quantify like specific compound without separation. So how do we separate different compounds in environmental samples? That's chromatography. Okay. So actually, chromatography is an ancient method. It's an ancient method. So probably like 100 years ago, I don't know exactly when, but a long time ago, there are researchers who invented, chromatography, and it looked like this. So this is chromatography, and it basically consists of a glass column, and then inside the glass column, you paint it with some solid material. Okay, solid material. And when you load your mixture of compounds into the column, the gravity would drive the mixtures of compounds, moving forwards. And when the mixtures of compounds is on its way from the from the top to the bottoms, they got separated. They got separated. So here comes the question. What during the when the mixture of compound is traveling from the top parts to the bottom parts of the chromatography, why can they be separated? 我们讲那个 chromatography，晨曦中文叫晨曦，它是一个古老的方法那这个晨曦管柱呢长这样子，它里面有一些这个固体的这个packing material。好，那当你把你的 mixture 这个 mixture 就是混合在一起的这个compound比方说它有5种 compound 混在一起，然后你把它这个load 进去，好，然后呢？这个重力呢，就会让你这个 mixture 呢开始往下流，在流动的过程中，它们自然而然就分开来了。那我的问题是说，为什么在这个过程中，它们可以被分开来？Let me repeat my question. So a chromatography is something like this, and you have some solid packed material inside. When you load a mixture compound into a column or a chromatography, the gravity is driving the whole mixtures moving down. And when this happens, when a mixture is moving downwards, compounds got separated. For example, if you have 5 different compounds in these mixtures, and when this mixture is flowing down, these 5 compounds got separated. Why? All right. So let's take another short break and come back. Hopefully, you guys are able to answer these questions.